Hello everyone, I'm Nan from UC Santa Barbara. I'm going to introduce our paper IronMan, GNN-assisted design space exploration in high-level synthesis via reinforcement learning. Just a quick recap of HLS. It is an automated transformation from behavioral descriptions in high-level languages to RTL designs. Despite the great success of HLS tools, we observe several unresolved challenges. First, high-level abstractions in HLS can conceal optimization opportunities. This is because the structured coding style in HLS makes it really hard for advanced or fine-grained optimization. Meanwhile, it usually requires manual or complicated efforts in code transformation to improve the performance of irregular logics. This table shows an example. This is a simple multiplication accumulation function using a for loop, which requires the DSP usage no more than 3. One typical way to do this is to unroll the loops as shown in line 2 to 4. One problem is when the loop boundary, which is 8 here, cannot be divided by the DSP constraint, which is 3 in this case, it results in a partial unrolling as shown in line 4, which introduces undesired increase of latency. But when the high-level abstractions are transformed into data flow graphs by code transformation, it is much easier to apply different pragmas to conduct finer-grained DSCs as shown from line 5 to 11. This provides a first motivation. As we are seeking for better performance and more flexible optimization choices, it is necessary to do code transformation. The second challenge is that HLS tools do not always provide the best solution nor the Pareto solutions. Existing DSE approaches, as well as commercial HLS tools, do not provide flexible trade-offs among different objectives or constraints, for example, different types of resources, and they usually sacrifice design latency for less resource or vice versa. This figure provides an example, and it shows the Pareto solutions between LUTs and DSPs. The red stars here indicate the Pareto solutions, and the purple dot is the single HLS default solution. In this example, first, the HLS default solution is not on the Pareto frontier. Second, there is a really large design space to find the Pareto solutions, and actually it grows exponentially with the size of DFGs, even for a binary solution between DSP and LUTs, let alone the consideration of different graph topologies and data precision. And thus, the DSE for Pareto solutions is non-trivial. Here goes the second motivation, the pursuit of the flexible and fine-grained DSE. The third challenge is that existing HLS performance predictors do not support irregular logic or data paths. So the third motivation is that we really want high accuracy predictions for both regular and irregular data paths. Based on the three motivations, I will introduce how IronMan is designed. Given the demand for code transformation, we propose a code transformer which breaks up the boundaries of high-level abstractions, fuses them into data flow graphs, and regenerates synthesizable C or C++ code with proper pragmas. Based on our pursuit for flexible and fine-grained DSE, we design a deep reinforcement learning-based DSE tool aiming to learn optimize the resource allocation strategies. As high accuracy performance prediction is also desired, we build a GN-based performance predictor, which leverages the inherent graph structures of DFGs and provides high accuracy predictions. While each proposed component can make contributions independently, we further integrate them together into an end-to-end framework IronMan. IronMan takes HLS C or C++ code and user-specified constraints as inputs, and outputs the transformed code with proper HLS directives. The regenerated code either meets the predefined requirements or provides Pareto solutions among different optimization objectives. Now let me use an example to demonstrate how IronMan works. Let's say we have an example code which is a for loop. The very first step is that this for loop will be transformed into a DFG by the code transformer. A DFG is a graph that represents data dependency among different operations. Assume that now we have a resource constraint of using no more than 2 DSPs. If nothing is done to optimize the DFG, the HLS will generate a default solution which uses 4 DSPs and has a latency of 3. One naive method is to directly apply the allocation pragma to limit the usage of DSP. This method does work, while it increases the latency from 3 to 4. An alternative is to apply the resource pragma to optimize the DFG, and this is how IronMan handles this problem. By treating off different types of resource, let's say using lots to compute multiplication instead of DSPs, IronMan is able to keep the latency unchanged and find optimize the resource allocation strategy that complies with user-specified constraints. Finally, after the optimization, the optimized DFG is transformed into C or C++ code with proper directives by the code transformer. This work as a case study of IronMan. The specific problem solved is to find a solution that either strictly meets DSP constraints or to find Pareto solutions between DSP and LUT without sacrificing the computation latency. Now I will introduce more details of our gene-based performance predictor GPP and RL-based DSC engine RLMD. Given a DFG extracted by our code transformer, each node is encoded into a 10-dimension node feature vector that represents a node type, the data precision, and whether a pragma is applied on this node. Then this DFG is passed through graph convolutional layers. Just a brief notice of GCN. In one GCN layer, each node in the graph aggregates features from neighbor nodes. The more GCN layers are used, the larger the receptive field is considered. Here, we use 2 GCN layers in our model. Next, the learned node embeddings are summarized by a mean pooling to create a graph-level representation, which is then passed to a feed-forward network to generate both the graph embeddings and the final prediction results. If we take a higher view of our GNN-based performance predictor, the left part summarizes the process of generating graph representations, and the right part shows the structure of the feed-forward network. We employ 3 GNN models of the same structure to separately predict the LUT DSP usage and CP timing. As GPP intimately cooperates with the following RLMD, it has 2 major goals. First, in RL problems, an informative and well-crafted state representation will greatly benefit the learning process. Intrinsically, DFGs are graphs with various topologies and sizes, so that graph-based representations are naturally suitable. We use GPP to provide graph embeddings of DFGs as state representations, such that the following RLMD is able to generalize across different graph topologies. Second, RL tools are notorious for long training time, and this will be worsened by frequent interactions with HLS tools. So we use GPP to provide high accuracy prediction of the actual performance, such that the solutions generated by RLMD can be quickly evaluated, thus accelerating the learning process. Then in RLMD, the resource allocation problem can be formulated as an RL problem. The input here is the DFG with no directive. What has been done here is to train a policy to decide whether to assign the resource pragma on each multiplication node. Once the entire assignment is completed, GPP will evaluate the resource usage and the timing of this solution, which are used as the feedback to improve the policy. So next time, the policy can generate better decisions and the resource usage will be optimized. This loop iterates many times until the policy converges. In this formulation, the states are basically the every possible partially assigned DFGs. The action at each time step is whether to specify the current node to be implemented by LUTs instead of DSPs. We define the reward to be 0 for intermediate steps, and at the very end, the reward is considered as a negative weighted sum of predicted resource utilization. To integrate RLMD with GPP, this is the structure of GPP shown in the previous slide, and we use the graph embeddings as part of the input to RLMD. In RLMD, we use the actor-critic method. Specifically, the state is a vector that involves both the graph embeddings and metadata of the graph. The action is generated by the actor, which is a probability distribution over valid actions. The reward relies on the predicted results provided by GPP. Let's move on to the experiment part. In the setup, we build a data set of both synthetic DFGs and real case benchmarks. For the synthetic part, we randomly generate 47 different topologies with 100 sets of directives per topology. This makes up 4,700 different graphs. For real case benchmarks, similarly, we generate 100 sets of directives per benchmark, making up 800 graphs totally. IronMan is compared against the several heuristic-based optimization methods, simulated annealing, genetic algorithm, and the HLS tool. To demonstrate the generalization capability of IronMan across different DFGs and applications, it is trained on part of DFGs from the dataset and evaluated on the rest of them. The ground truth used in this work is synthesized by Vivado HLS and implemented by Vivado. It is noteworthy that GPP provides predictions of the actual resource utilization timing after physical synthesis. Here present some results. GPP predictions are compared with HLS synthesis reports regarding LUT, DSP, and critical path timing. The dots in red and green are the predictions provided by GPP, and most of them reside on the line y equal to x. The triangles in blue and orange are the HLS estimations. On average, GPP reduces the prediction error of Vivado HLS by 10.9 times in resource and 5.7 times in timing. This figure compares RLMD with GA and SA regarding the Pareto solutions between LUTs and DSPs. Obviously, RLMD outperforms GA and SA by a large margin. Given the same number of DSPs, RLMD is capable to find solutions reducing the LUT utilization by around 13% compared with SA and GA. After performing fine-tuning, additional 11.6% reduction in LUT utilization is achieved. These promising results show great potentials of applying reinforcement learning for DSE in HLS. We then fully evaluate IronMan performance on real case benchmarks. Among 4 real case benchmarks with 40 different DSP constraints in total, IronMan is able to meet 39 of them and can further improve to 40 by fine-tuning. Specifically, IronMan can perfectly match the target DSPs, whereas those solutions found by SAGA and Vivado HLS consume much more DSPs. In terms of the latency, IronMan always keeps the shortest latency, while Vivado HLS increases the latency by up to 6 times. To conclude, IronMan is an end-to-end framework, which aims either to help HLS tools generate higher quality solutions under constraints, or to perform more flexible DSEs to provide Pareto solutions. IronMan is equipped with a GN-based performance predictor GPP, an RL-based DSE engine RLMD, and a code transformer. Independently, GPP achieves high prediction accuracy. RLMD obtains Pareto solutions surpassing GA and SA. Integrated, IronMan is capable to perfectly satisfy user-specified constraints with up to 400 times faster than the heuristic algorithms and HLS tools.